So there's been a couple of questions associated with homework 4. So I thought that I would take a minute to talk to you about that. So here's this floor slab system, okay? So you got this overall floor like that, going around like that. And then we've got these beams, floor beams going like this, right? And then you've got these other girders that are cutting across this direction, right? And so the first part of the problem says, design a continuous concrete floor slab for this application, determine the slab thickness, and select the reinforcing bars to be used in the slab. Jury results in a final sketch. Use grade 60 steel and 3,500 psi concrete. Include consideration for shrinkage and temperature steel. So, just the first thing you got to do is you got to figure out which direction this thing is going to be spanning. Right? It's going to be spanning the short distance. Right? We talked about in that class the stiffness attracts load and things of that nature. And so, it's going to be spanning like this. Okay. Over this, right? Across, I guess it's just all the way across each of these, across these beams, okay? And so we're designing the slabs, and what we're going to design is a 1 foot wide slab that runs across this direction like this, okay? Very similar to the homework or the example problem we did in class, okay? And so that's what's happening there. So that's the first part to figure out, and we just discussed that. The second part of it, right, because all we're doing is design the slab. So, these other dimensions, right, these dimensions like this 18 foot and stuff like that, that would apply if you were designing, right, these beams going across, right, these girders that are going across, catching these floor beams. And if you're designing these floor beams like this, you'd have to deal with that. But we're just designing the slab, so we're just going to have this sucker going across like that, okay? So then the other thing that came up is they give us a little section, right? Well, what's happening with this section? So we're going to take a couple minutes to discuss that with you, right? And so what this is, right, this is a section at the wall line, and you could be looking at it this way, right? Or since we're designing the slab, let's think of it as this little section that's looking like this, right? So you're looking at it, well, probably in the wall actually, so it's looking like that. Well, I'm gonna just draw it. It would be, right, if we were looking like that on the wall, and how was that slab connected to that wall? And so that's what's happening over here, is how is that slab connected to the wall? And so here is the wall. Try to maybe make that in red here. So this is the wall. Going through that like that, right? And then this beam is coming into the wall. It's embedded into the wall, right? And I would say that it was cast integrally with the wall, right? That's attached in there. It has wall above and below. It's going to restrict some moment in there. So I would say that it was cast integrally with that wall. And so that's what's happening right there. And so here's the beam is going embedded into the wall. And then it's showing you where the center line of the bearing is, right? And so that's what this is showing us right here. There's the center line of the bearing. So this thing, there's the beam sitting in here, and it's resting on a bearing, right? And so that's where its effective bearing force would be coming in right there. Why that's important is because that tells us, right, when you draw shear and moment diagrams and stuff like that, it's going from the center of the support to the center of the support. So it's the center line of this support to the center line of this support over here. And so they give you 2110. The 2110 is from the outside of the wall to the center line of this beam over here, right? So if you look at this right here, it's going from 2110 outside of the wall to the center line of this interior beam right here, okay? And so from that, and given this 10 inches right here, we can determine, so it's 2110 from outside to center line. So 21 minus 10 inches would give us from center line here to center line here. So it's 21 feet from center line to center line there, okay? So that's the 21 feet is that, okay? But then, when we're designing our slab, we're going to design our slab, just as this section right here, it's going to span from here, and it's going to span to across this beam, and then across this beam, and then across this beam right here as it goes across. So really, the span that we need for designing our slab is going to be this 21 feet divided by 3, right? Because you have a span here, and, well, from center line to center line, from center line to center line to center line to center line. Those are 21 feet. And so it's 7 feet for center line to center line between here and here. Okay. And so that's that 7 feet. But then we got to come in to the face of the support because to use LN, so the LN is the clear span distance, not the center to center line. It's the clear span distance between the beams. So the clear span distance is going to be 7 feet minus. So this is, they give us 5 inches, 15 inches minus 10, and so this distance right here is 5 inches, and so it's going to be 7 feet minus 5/12 of a foot minus 6/12. So where does the 6/12 come from? Well, this thing is 12 inches wide, and so you're going half of that direction, so that's 6/12, and so that's what your clear span is there. And then this clear span is 7 feet minus 6/12 as well. All right. So this one, sorry, for this other span over here, this is going to be 7 feet. That's just 7 feet from there to there, minus 6/12, minus 6/12 to come to the face of both of those supports. So the span lengths are slightly different, but pretty dang close to each other. Okay. The other thing to note is that they're both under 10 feet. Okay, and so if you look at that table, the shear and moment coefficients, I think 10 feet triggers different shear and moment coefficients. So, if you go through the problem and you didn't notice that less than 10 feet span, I think it's 10 feet. Let me see. Columns, continuity slabs. Moment coefficients is a face of all support satisfying slab with spans not exceeding 10 feet. So there's a simplification you can use there. If you do it the other way, right, that's totally fine. But that might be a little bit easier to do if you notice that spans less than 10 feet. Okay, so the first part of the problem is almost identical to what we did in class for an example. Okay, in the class we did as an example, we just designed this thing for, we set the depth based off of deflections. We checked to make sure it was okay with shear. We then went and looked at our shear and moment coefficients as we move across our moment coefficients as we move across the beam. What's the moment here, in the middle, here, right there, in the middle, right, as we go along. And then we put it into a spreadsheet in order to design and check those capacities and things of that nature. Okay, and then. So making that little spreadsheet and working out those details would be good for you. Okay, or actually is part of this problem. That would be good for you. It would be good for you. What am I talking about? Okay, it'll be a good experience for you to hone your Excel skills. Okay, but that's what I'd like you to do is make a little spreadsheet to check those capacities. Then you select the steel, and then you check it compared to the limits. There's a minimum amount of steel reinforcement required, the area of steel, and then there's a max spacing of that reinforcement. And the last part is you have to design the shrinkage and temperature steel, which the shrinkage and temperature steel is going this way. We're putting it this way for strength, and the top and bottom as we move across. In this direction, we're putting it for shrinkage and temperature. So that first part should be pretty straightforward, with the exception of maybe making the Excel spreadsheet, but that's also not too bad either. The second part says, design alternative has been suggested that will use precast concrete floor slabs 7 feet wide and 21 feet long instead of the cast in place slabs. Compare the maximum positive and negative moments that you use in your slab design with the values that you would use for simply supported precast slabs. And so the idea would be is that you would come in and you would, instead of doing a big cast in place, you would come in with these precast panels that are 21 feet long and 7 feet wide. And so you'd have a precast panel there, and then you'd come in and set it next to a precast panel here. And then you'd set down another precast panel on top of that, and then you'd have another one here, and then you'd have another one here, and then you'd have another one here. Okay, and then so on across the whole thing. So you'd have all these things precast, and you come back and put it into place. Okay, and so even if it's precast, you would design it to span across this short distance, right? Except for it's precast, right? If it's precast, that just means that if you were to look at that that same cross section right here, it'd be this, it would be like if you looked across like this, right? It would have, it would just be, think of it like have a bearing, just like a thing set up like this, and then you would have a precast slab that you would cast on top of it. right? And then there wouldn't be continuity. There'd be another one right next to it like this, right? Another one next to it like this as you move across. And so they're just sitting there. And so one thing you may notice is as compare it to the negative moments. Is there going to be any negative moment there? Right? Think about that. Would there be any negative moment if you just place this slab panel and place it next to another slab panel as you move across, right? The answer is no. Okay, there will not be any. There won't be any negative moment. It's just that's a simply supported beam spanning across that direction. Okay, and so, but compare those moments associated with that, and then. Yep, that's it. And then a colleague commented that if you precast panel is used, you might have to be careful about how you lift these things. And so I want you to think about that a little bit. Is right if you have a big slab section, right, like that, and you have one right next to it, and so forth as we go across. Why do you have to be careful about picking those things up, right? And I want you to think about that a little bit and write about that, right? And it has to do with, I always like that. I pose a question for you and then I feel the need to answer it immediately. But it has to do with when you come in and pick this thing up, right? What your inclination would be to grab it here and to grab it here, right? And pick it up like that. Have some crane over here. Oh, I want to see a crane. There's my crane, and I'm lifted this thing up. Right? You have an inclination. That's terrible. You get the point. You have a crane that wants to lift it up. Is it bad if you lift it up like that? Okay? Think about that a little bit. Right? Is it bad? I'm gonna put some wheels on it. Yeah, now it's starting to look like a crane, a little box. There we go. Damn right. Like that. Okay, we're gonna lift it up. Picking it up like that. Is there a problem when you do that? I want you to write about that a little bit. Okay. All right. If you have any other questions.